this video, I want to look at the application of our consideration and discussion of momentum to general planar motion. So general planar motion, as compared to what we've talked about already with linear translation and fixed axis rotation, is comparable. However, the key aspect of general planar motion, when we consider it as a basis for how an object is moving, is that we both have velocity, linear velocity of the center of gravity, and rotation. And the key difference is that we don't necessarily know that the velocity g is equal to the distance between some rotation axis and the angular velocity. So there's kind of a slight disconnect there compared to fixed axis rotation, in that the axis that we're rotating about is not necessarily fixed at any point in time. That axis itself is potentially moving. So we're going to apply this scenario of general planar motion, where there's some linear translation and some rotation occurring at the same time. And as such, we again will calculate our values of momentum, linear momentum being mass times velocity, as we've already seen, angular momentum about the center of gravity, not changing at all, mass moment of inertia times angular velocity. Now, if we want to take the mass moment of inertia about a different point, so let's specify some new point out here, A, and say, well, how about we want to know the angular momentum about point A? Well, in this case, we can say, much like we saw before, we have to take into account the angular momentum around the center of gravity, and then we have to add on some term that accounts for the fact that A is not located at the center of gravity. So I'm going to write this in the form of dmvg, where d now is the distance between my velocity vector v sub g and my point A. However, it's not just the straight line distance, it's the distance between the line of action of that vector vg. So in this case, I would draw a line in here, say that that's perpendicular to that, and then this gives me my distance d that I would use for that calculation. Another slight variation on this is that if I go back to what I said at the beginning, is that general planar motion means that there is both translation and rotation, and the point about which the object is rotating isn't fixed in space, and it's itself moving. However, recall that we have something called the instantaneous center of rotation, which means that at any instant in time, there is a point in space about which any motion can be said to be fixed axis rotation. So if we can locate that instantaneous center in the same way that we've talked about before, we can also calculate the momentum about the instantaneous center using the mass moment of inertia about the instantaneous center and multiplying that times the angular velocity omega. Now, just like we've seen before, I could figure out what this mass moment of inertia about the instantaneous center is by using the parallel axis theorem. So kind of the first step is locating the instantaneous center, which we've talked about before, and then using parallel axis theorem to compute this new mass moment of inertia, which allows me to get angular momentum. And what that allows me to do is treat the problem as a fixed axis rotation problem, knowing that that instantaneous center, though, moves through space as the motion progresses. All right, so we'll stop there. Thanks.